So we have seen already that we can consider the acceleration due to gravity as being constant close to the Earth's surface. And in this video, we will work out an equation of motion for this scenario where things move under gravity on Earth. Before Newton, others had done similar work on how things move, especially Galileo, who had worked out that objects falling under gravity tend to speed up. And he worked out the relationship between distance moved against time for falling bodies. Galileo also worked out that bodies move in a parabolic arc under gravity, as we shall see. But it was Newton who solidified these ideas into concrete theories backed up with mathematics. And most of this was contained in his book Principia, which is why that is such a landmark achievement. Newton's laws of motion and his calculus allow for some simple equations to be formulated which can be used anywhere when an object is falling or moving close to the Earth's surface. And we will now derive these equations. So to remind you, we are doing the case of an object moving close to the Earth's surface under gravity only and with no other forces present, so no air resistance or friction. We know that the acceleration due to gravity g is constant near the Earth's surface and its value is about 10 meters per second squared, so we will use this fact. We will also assume in a general way that our motion is between 2 times t1 and t2. But as we've seen before, we are allowed to simply say that our start time is t equals 0. So we will say that our time interval is just t. This will keep things simple. Let's start with the expression for acceleration. And we saw previously that a is given by the rate of change of velocity, so a equals dv by dt. Now we'll use calculus and integrate both sides of this equation with respect to t, and we get this. On the left side, we know that acceleration a is constant, so that comes out of the integral, and the definite integral between times 0 and t just gives us t. So on the left side, we get a times t. On the right side, the dt's cancel, and we're left to integrate dv between times 0 and t, which gives us the velocity at time t minus the velocity at time 0. We can call the velocity at time t as being v, and the velocity at time t equals 0 as the initial velocity, and we'll call that u. So we end up with the expression at equals v minus u, and we can then rearrange this to get v equals u plus at. And this is our first equation of motion. Now let us do the same exercise for the expression for velocity, which we know is given by the rate of change of displacement with time. If we integrate both sides with respect to t, then we get this expression. On the left side, we already know an expression for v, which we have just derived, so we can replace that for v on the left side. On the right side, the dt's cancel, and we're left to integrate dx between times 0 and time t, which gives us x2 minus x1. If we now integrate the left side, we get ut plus half at squared, and the right side is just s, the displacement, the difference between the start and end positions of the move. So rearranging this expression gives us the second equation of motion, s equals ut plus half at squared. We can also use these first two equations to come up with two other relationships by substitution and rearranging the variables, and we end up with these four equations. These are commonly known as the SUVAT equations because they use the 5 variables of motion, s, u, v, a, and t. Note that in each of the 4 equations there is one variable missing, and this means that if we don't know or don't want to use one particular variable, then we can pick the appropriate equation to work things out anyway. Now let's use the SUVAT equations to work out how something moves. In this example, we'll look at the motion of an object like a ball or a projectile being thrown into the air. When considering motion like this, it is always helpful to draw out what the motion looks like in a general way, not least because it helps to make clear the positive and negative directions of motion. So this is our diagram of motion, and we are saying that we will make our start position and start time to be both 0. So x equals 0, t equals 0 at the start. We know we can do this because it does not affect the calculations as we've seen before. We will say that motion upwards in y is positive and motion to the right in x is also positive. Gravity acts downwards with a constant value g, and since g is acting downwards, it will have a negative value, which we will need to keep in mind. The object is thrown at an angle theta with respect to the ground and at an initial speed of u. At any later time t, the object is said to be at a position x moving at a speed v. And we will assume no other forces like air resistance are present, and this is our setup. Firstly, let's consider the initial velocity u, and we can draw it like this. U is a vector at angle theta with a magnitude u. And so we can split this into two vector components along the x and y axes. The components along each axis can then be written like this using basic trigonometry. Now let us use one of the SUVAT equations, and we will use the one for displacement. But we want to look at the motion in x and y directions separately. So let us make two equations for the x and y directions, and we can use the components ux and uy to denote the initial speed in the x and y directions. In the same way, we can define acceleration in the x and y directions as having components ax and ay. Now we have assumed at the start that g is the only acceleration and it acts purely downwards in y. So we can say that there is no acceleration along the x-axis, hence ax equals 0 and ay equals minus g. Putting all of this together, we get these two expressions for motions in x and y directions. From the first of these two expressions, we can rearrange to get an expression for time t. And then we can put this expression for t back into the second expression for y, and we get this relationship. After simplifying, we get the final equation of motion, which gives us the expression for y in terms of x, theta, and u. Note that this equation does not depend on the mass of the object, so it does not matter what is being thrown. We can use this expression to work out what will happen to any object of whatever mass. Now, let's use this equation of motion to work out some useful things. First, let's see how to work out an expression for how far the object will travel, that is, its maximum range. We can take the expression for y, which we have just derived, and factor out x on the right-hand side. Now we know, and can see from our diagram, that when the object hits the ground, y equals 0. So we can say that the right-hand side of the equation equals 0. So we need to work out what the value of x is when y equals 0. We know that at the start x equals 0 and y equals 0. We define this as our starting condition. So that must be one solution to the expression. And this takes care of the x outside of the brackets. This means that what is inside the brackets must also equal 0 for the other case when the object hits the ground at the end of its travel. Hence we can say that the tan theta must equal this expression. Now we can rearrange this expression to get a new expression for x. And using a relationship for cos and sine theta, we can finally get the expression for the maximum range of x. Looking at this expression for maximum range, we can see it contains a sine 2 theta term. We know that the maximum value of a sine function is 1. So for x to be maximum, the value of sine 2 theta must be 1. Since sine of 90 degrees is 1, this means that theta must equal 45 degrees. We can sort of guess this is going to be correct, that if we launch the object at 45 degrees, it will go the farthest. Any lower or higher angle will fall much shorter. That is the intuition, but we've just proved using our equation of motion that 45 degrees is indeed the correct angle to use to get the maximum range. And if we put in some numbers, then we can see that we can work out the actual expected distance if we throw the object at an initial speed of 10 meters a second at 45 degrees, then it will travel a maximum distance of 20 meters. Now, let's see how we can work out an expression for how high the object will travel, that is, the maximum height. And again, we can draw the scenario and write down the equation of motion so we know what we're going to use. Now, when the object is traveling upwards, it is going in a positive direction. We said that at the start. And when the object is falling downwards, then we know it has changed direction and it is moving in the negative direction. So at the top of the motion, the object must come to an instantaneous stop when its direction changes from positive to negative. So at the top of the motion, we can say that its speed is 0. Hence, its rate of change of height is going to be 0 at the top. So we can say dy dt equals 0. This means that we can differentiate the equation for y to get an expression for dy dt, and from this we can find an expression for the time t at the top of the motion. So this time t is the time at which the maximum height is reached. And we can now replace this expression for t back into our equation of motion, and if we arrange and if we simplify, we get the expression for the maximum height. And if we put in some numbers again, we can get an answer, in that case to be the maximum height of 2.5 meters. Finally, let's go back to Newton's apple tree and just see how we might use the SUVAT equations to work out what happens to the apple. Let's assume our apple is 10 meters high and falls straight down. If we assume that only gravity is acting on the apple, then we can use our SUVAT equations because they apply when we have constant acceleration. And we can say that the initial velocity u is going to be 0 because the apple is at the tree, on the tree. And we know g equals minus 10 meters per second squared. So in this setup, what we want to know is how long does the apple take to fall to the ground, and what is the speed of the apple when it hits the ground. To work out these two things, we can use two of the SUVAT equations. First, to work out the time that the apple fall takes, we can rearrange the equation for s to give an expression for time. And then we can work out the time using our conditions. So s is the displacement and is 10 meters, and acceleration due to gravity is minus 10 meters per second squared. This gives a time of 1.4 seconds. Now we can use the equation for v and use the time t that we have just worked out. And we get the answer that the apple hits the ground traveling at 14 meters per second. At the beginning of this video, I had said that Galileo had worked out that objects fall under Earth's gravity in a parabolic arc. And we also have shown this when we derived the equation of motion. But let me point out this more clearly. We worked out how a projectile moves when thrown under Earth's gravity, and we obtained an equation of motion. When we look at this equation, we can see that this is what is known as a quadratic equation, meaning that it has x terms up to the power of 2 in it. A general form of a quadratic equation is y equals ax squared plus bx plus c. And in our equation of motion, the a coefficient equals minus g over 2u squared cos 2 theta, and the b coefficient equals tan theta, and c is 0. So our equation is a quadratic equation. If we plot this equation of motion, then we get a parabola, which shows that Galileo was correct. All motion where things move just under the influence of gravity is parabolic motion. So when we throw a ball in the air, it will go up and come down in a parabolic arc, assuming no air resistance, of course. Galileo worked this out some 450 years ago. So to summarize, we have not only shown how we can derive some equations of motion, the SUVAT equations, but also how we can then use them to get actual answers to questions like how far will something go and how high will it travel before it comes down to Earth. And in the case of the apple, we worked out how long a fall might take and what will be the speed on impact. In any situation on Earth, we can work out how things will move if we know enough about the conditions. And Newton's laws of motion and his principles of how things move under gravity can be used to work out these things. Although we have not done it here, we can extend the same principles to include air resistance or other forces if we need to. The equations get a lot more complicated, but nonetheless we can work out new expressions for how things will then move. In the next video, we will go outside of the Earth and do a similar exercise to see how things move in space. I hope you found this video interesting, and until next time, keep thinking physics.